Okay, so let's see. So here is the definitions that many reactions can produce two or more than two stereoisometric product. But if we show preference of- for the one stereoisomer over the other, then we say that the reaction is stereoselective. Example is here. You can see here that you see this hydride is acting as a nucleophile, right? Hydride is acting as a nucleophile. It can attack on this carbonyl group by two ways, either on the side or on the rear side. But one side of the this carbonyl group has been blocked because of this bridge carbon. So it means that if a nucleophile is approaching here, there will be a resistance offered by this bridge carbon that will not allow a frequent visit of this nucleophile to this site. But on the other side, there is no resistance. That's why it will can easily come and attack on the other side. So that's why there will be a differential product. The path or the side where there is a resistance that gives the lesser product, that is 14% of the product. But the other side where there is no resistance, it gives the 86% product, right? Some more example. What about here? Example of these are some more example of the stereo selective reaction. You can see that this is a nucleophile. This nucleophile can attack on this carbonyl group. Now you will be saying that, sir, it is quite far away. Why you are saying that this can make and can affect the attack on this carbonyl group? This can be clear when you draw the chair conformation like this one. The chair conformation, you can see that this is coming quite closer to this one. That can affect this nucleophilic attack on this side. So there's two possibility. When you draw the chair conformation, if this group is equatorial to this one, I mean they are far away from each other, then the reaction will be more feasible and you will get this kind of product. But if this is not equatorial to this one, then you will get this kind of the product that will be very less in quantity. So it is evident from here, right? So preferential, we can draw the chair conformation for this. This is just like the cyclohexane, where the this bulkiest group can be, favorably placed at an equatorial position to this one. I mean, this will be at equatorial and trans to each other. That will be the preferential stereochemistry for this one. And you will get the one of the product will be predominant at that conditions, but the other product will be less. What about here? So you see, this is the Grignard reagent, and this carbon is acting as a nucleophile. Now, as I said before, there is a stereo center here. See this stereo center, and there is the bulkiest group. There's this phenyl group that can decide the overall stereochemistry of this group. If this phenyl group is directed towards the other side, the attack on this side will be more feasible. But if the phenyl group is directed to this side, then the other side attack will be most favorable. So when you draw so how do we know that the phenyl group is on the other side or on this side? You know, you may have experience of using the Newman and Sahor's projections. Have you ever try on that? If you draw that, you will see that you can, bring this far more away, trans to this bulky phenyl group can be bring at far more away from this one. Uh, so that's possible. So if you do that, after that, you will see that the attack on this carbonyl group on the side that is far away from this phenyl group would be giving predominant product compared to the one where this phenyl group is directing towards this. Is it? Yes. Just see it. So this OH formation is taking place On the back side, it means that the attack has taken place over here, right? Why it has been attack taking place over here? Because the bulkiest group is on the other side. So this can be same as the below example. In the below example, you can see that one of this product is, in this example, you can see that what has happened. The uh, hydride has attacked on which side? On the other side. That's why the on this side. That's why the OH has gone below the plane. And this is 96% of the product. So there's selectivity. This attack on this carbonyl group from the front and the reverse side is not equal. One is more predominant over the other. So just move ahead. Let's see. Now look at here. We have two groups. Possibility in place of this X, we can use try this one or this one. So if we are using this one, which is not so much bulky, then what would happen if we are doing the hydrogenation? Then this bond will hydrogen can add on the front side. If hydrogen is added on the front side, so we get 94% of the product. There is no problem. And on the other product where the hydrogen will be below will be only 6% because this group is not too much bulky. But if you are using the bulkiest group over here, it will definitely have the steric interaction with the coming hydrogen. So then it will be, then what would happen? Then under that condition, this product means where this hydrogen is coming the way to this group is only 15%, 15%. And the major product would be this one, that hydrogen would love to come from the rear side to from the opposite side to this group, right? So same is the below example, and you can see their variable percentages of the product. They can give variable amount of that product. What about here? You can see here that you see that if we are attacking on if we are hydrogen if we are subjecting this to the hydrogenation, what would happen? The hydrogen can add on the side, on the front side or on the back side, right? But if it is added on the front side, and if we are interested only in this product, if we are asked to have to get only this product and avoid the other product, because under that condition there will be a racemic mixture because this is sp2 carbon, there's possibility for both of the product 50-50%. And if we are asked by our professor that no, we do not need the other product, we only need this product, so how to do that? We can use this masking agent. This is the sort of the agent that can control the stereochemistry at one side so that preferentially we have one product. So you can see that if you put it this way, this will be attacking on the hydrogen hydroxyl group, and it will be at it will get itself attached to the hydroxyl group, and it will definitely block one side, the other side, and definitely we would have these enough space for the hydrogen that can come preferentially on the front side because the back side has been blocked by this one. This will be directed towards back side, this whole group. So that side is blocked, so the hydrogen would have preferentially the front side. So if we are putting it here, the front side, back side would be blocked, and hydrogen can favorably attack on the front side, and we will get 99% of this product, right? So this is called in enantioselective selective reaction. We can get 100%, almost 99% of one of the product. The other product will be negligible. C99 run ratio 1. Why I'm saying that this is enantioselective? Because there is a generation of the stereocenter, right? And a generation of only one stereocenter after the attack. There is no pre-existing stereocenter. If there would have been any stereocenter before, the reaction would have, I would have called that as a stereoselective, right? But this is not stereoselective, it's enantioselective. Okay. So what about here? Again, if you see the this already existing group, if it is, you can try variable functional groups, starting from the very simple to the very bulkiest groups. The more it is bulkier, the higher will be the selectivity, right? As you are trying, this one is the bulkiest group, this is even bulkiest. So if you are using the bulkiest group, what would happen after the hydrogenation? The stereochemistry of this and this would be trying to be far more apart, as far as possible. They will try to orient themselves far more apart from each other, and that would be possible if the groups are there. They are small, then it's okay. But if they are bulkiest group, they would try to push themselves away from each other. This can be, you can check this by drawing the chair conformation for that, and then put this. You will get a better idea how to make them away from each other. So this is again the stereochemistry that orient the coming group, direct the coming group. What about here? Again, for controlling the stereochemistry at one side. But here, the only difference is that here there is already an existing stereocenter, right? So now, if whatever the attack is happening over here, after the generation of the next stereocenter, the reaction we can call as a diastereoselective, because there is a diastereomers will result after the attack from at first is at first instant at one side, and on the other instance on the other side we will get two product, and the two product would have will have the diastereomeric relationship to each other. Based on that, we can call this center as a diastereo. This reaction is a diastereoselective reaction because there is a selectivity, diastereoselectivity in this reaction. The preferential attack would be at one side because of the uh, because we can mask, if we try this one and put it here, derivatize this OH group with this one, the one side will be masked altogether, and there will be a physical feasible attack on the other side. For instance, if I am blocking this one, right, and the back side would be completely blocked because this is going back side. So the back side is blocked, there will be a preferential attack on this on the front side. That is how it is. So we can see some more examples. Similarly, you can see here, this is what I was trying to say, that if this, you know, this is a carbonyl group. See, this is a carbonyl group, and the attack of the hydrogen, uh, if this is coming this way, right, equatorial to this one, what do you think? There will be a steric hindrance, is it? So here you can see that if we place it here, the carbonyl group has too much steric hindrance from the axial hydrogen from every side. That's why this uh, uh, if the coming nucleophile uh, would try to attack from the side, that so that this become the equatorial in positions, so that will adopt the orientations at the equatorial positions, because if it is orienting towards the axial position, there will be an extreme level of the steric hindrance because of these axial hydrogens. So you can read all these details of this. Same as the hair, you can see that the carbonyl group and the steric handles offered by the rest of the ring. See, I can tell you one thing else. In the pure chair conformation is only possible when you have the cyclic cyclohexane. But as you are, putting heteroatom in the cyclohexane ring, like the cyclohexanone or the other, there will be a slight distortion from the chair conformation, and this is what is happening. This is not in case of the cyclohexanone or cyclohexanol, you would not see that proper chair conformation. There will be a complete or a little bit distortion from the standard chair conformation. So this is the actual picture. You can see that the actual structure. But in either case, you would see that the attack on the carbonyl would take place, and the coming group uh, would attack in such a way so that the groups that is resulting get the equatorial orientations. Here it can be evident from this example. See, there is a this the this is a bridge carbon, right? So it is offering a resistance, so the carbonyl would love to attack on the other side. See this one, see this one. Again, there is a steric hindrance offered by this one. So this is sterically more hindered. One side is sterically hindered. So preferentially the attack wouldn't be on the other side. These are all the examples. See here, this group is more favorable lying if it is on the equatorial position rather than axial. What about here? These are sterically, are they not hindered? What about here? More sterically hindered. Preferential attack or one side. Here, preferential attack. So you can see the endo and exo product. You already know about the Diels-Alder reactions. You may have studied such kind of the compounds. Let me tell you about the stereospecific reaction in the next video.